Did you know that an experiment carried out over 50 years ago could be hiding secrets that the government doesn't want you to know about? What I'm going to tell you today is very real. In 1971, two physicists, Joseph Hafele and Richard Keating, decided to test Einstein's theory of relativity in a very peculiar way. They put atomic clocks on commercial airplanes and sent them around the world. The idea was to measure time at different altitudes and speeds, something which, according to Einstein, should result in small variations in the passage of time. But were the results of this experiment really what they told us? Or is there more to the story that has yet to be revealed? Stay with me until the end of this video to discover the hidden truths surrounding the Hafele-Keating experiment. The Hafele-Keating experiment was no simple prank by bored scientists. It was carefully designed to test one of the most fascinating predictions of Einstein's theory of relativity: time dilation. According to this theory, time can pass differently depending on the speed at which you are moving and the gravity you are experiencing. To carry out the experiment, Hafele and Keating equipped commercial airplanes with very high-precision atomic clocks. These clocks were sent to fly around the world in opposite directions, east and west. Meanwhile, other atomic clocks remained on the ground, serving as a reference. At the end of the experiment, the clocks that flew were slightly ahead or behind the reference clocks, as predicted by relativity. These results, at first glance, were in line with the predictions of Einstein's theory of relativity, which suggests that time passes more slowly at higher speeds and in stronger gravitational fields. However, not everyone was convinced. Some critics pointed out possible errors in the experiment, while others wondered if something else might be influencing the results. But what does this mean for us mere mortals? Well, if we could travel at incredible speeds, like the planes in the Hafele-Keating experiment, we would literally be traveling through time. Will we be able to manipulate time to our advantage in the future? And what would the implications of this be for our daily lives? Time dilation is not just a theoretical curiosity. It has incredible practical applications. For example, the GPS system we use every day depends on relativity to work properly. Without these adjustments, our navigation devices would be wrong by miles. These findings had a significant impact on the scientific community, as they provided one of the first experimental confirmations of time dilation. What's more, the implications of the results go beyond theoretical physics. They affect practical areas such as satellite navigation and the synchronization of communication networks. However, controversy persists, and this is where conspiracy theories start to come into play, suggesting that the results may have been manipulated or misinterpreted to hide even deeper truths. Just imagine, you're flying at 30,000 feet, and somehow your watch starts to slow down. And these results weren't just a coincidence. They provided one of the first experimental proofs that time is, in fact, relative. Conspiracy theories suggest that the results of the experiment were manipulated or that crucial information was omitted. One of the most intriguing theories involves the propagation of photons through space. Some believe that photons, as they propagate, lose time at each point of propagation, resulting in an increase in wavelength, known as a redshift. This idea challenges the notion that photons don't experience time, suggesting that they carry information on their journey, including the DNA of the planets they pass through. Could these tiny particles be telling us stories that we are not yet able to understand? The redshift phenomenon is widely studied in cosmology and is closely linked to the expansion of the universe. When we observe the light from distant galaxies, we notice that their spectrum is shifted towards the red, indicating that these galaxies are moving away from us. This is key evidence for the Big Bang theory, which proposes that the universe is expanding from an extremely hot and dense initial condition. There are different types of redshift that help explain various phenomena in the cosmos. 1. Cosmological redshift. This results from the expansion of the universe. As space expands, it stretches the light waves traveling through it, increasing their wavelength and shifting them towards the red. 2. Gravitational redshift. This occurs when light escapes from a strong gravitational field, such as that of a star or a black hole. The light's energy is stolen by gravity, which lengthens its wavelength. 3. Doppler redshift. Similar to the Doppler effect we perceive with sound, this redshift happens when a light source is moving away from the observer. The light emitted by the source shifts towards the red, indicating that the source is moving away. These redshifts are evidence not only of the expansion of the universe, but also of the interactions between light and gravity. In addition, they allow us to study the composition and history of the universe. For example, by analyzing the redshift of galaxies, astronomers can determine their speed and distance, helping to map the structure and evolution of the cosmos. By thinking of photons as carriers of information about their path, we are opening the door to fascinating speculations. Photons that travel for billions of years carry with them the history of the universe, from the cosmic background radiation, which is a remnant of the Big Bang, to the light emitted by stars and galaxies at different stages of evolution. We still don't have enough technology or knowledge to decipher all the stories these photons can tell us, but we continue to make progress. With instruments such as the James Webb Space Telescope, we are getting closer to unlocking the secrets of the universe, capturing light from very remote times, and observing phenomena that were previously invisible. As we talked about earlier in the Hafele-Keating experiment, the planes flew in opposite directions, one to the east, accelerating in relation to the Earth's rotation, and the other to the west, decelerating in relation to that rotation. According to the theory of relativity, the clock on the plane flying east, at a higher speed, should be ticking slower, while the clock on the plane flying west should be ticking faster. And that's what the data showed. But does this confirm Einstein's theory, or is there something more hidden? This is where things get really interesting. When we look at the data, we see that it can be interpreted in various ways. We accept that speed affects the rate of the clocks, but not necessarily that this confirms time dilation as Einstein proposed. Have you ever thought that we could be interpreting the data the wrong way? Consider this. If we have two clocks moving in space, each in a different inertial system, special relativity suggests that A's clock appears slower to B and vice versa. This is an obvious contradiction. What's more, the data from the Hafele-Keating experiment shows that the effects depend on the absolute speed in relation to a preferred reference frame, and not just on the relative speed. This defies special relativity. Another point to consider is the comparison with GPS. In the case of GPS, the clocks on board the satellites are continuously adjusted to compensate for the effects of time dilation, making it easier to see changes in the rate of the clocks as a function of speed. In the Hafele-Keating experiment, we start with all the clocks synchronized on the ground. Then, when the planes return, we clearly see that the clocks have accumulated time differently. Why is this important? Because it shows that the clocks really do change their tick rates based on speed, but not necessarily in the way that special relativity suggests. The observations show that the rates are asymmetrical, which is not consistent with the time dilation of special relativity. And GPS confirms this. So why is Einstein's interpretation still accepted? Why don't the world's brightest physicists question these obvious discrepancies? Perhaps in 100 years' time, scientists will look at this question with more focus than they look at special relativity itself. Science is always advancing, and it's natural for one theory to be replaced by a better one. And now, I want to know from you. What do you think of these theories? Do you think there is information being hidden? Subscribe to the channel and leave your comment below and take part in this discussion. In the next video, we'll explore another intriguing theory about the universe. Stay tuned, you won't want to miss it. Until next time, and keep questioning and exploring the world around us.